So we are on page 12 today. And we're going to start by talking about the world population. So at the top of page 12, we've got a little table here where we're going to take a look at a population calculator. And we're going to look at, over the course of a minute, how does our death total change and how does our birth total change? So I have a calculator, I think it's called a population world clock, pulled up here. And we can see here our current world population. We can see that it's ever changing. And we can even see in some cases where it sort of flickers back and forth between two numbers. And that's because we also constantly have people being born as well as people dying. So we can see those numbers just for today, as well as for this year to date. So we're almost 2 months done with 2021. These are how many people have been born this year. These are how many people have died this year. And then again, our numbers just for today. So we're going to start today by taking a look at how many births we see over the course of a minute, as well as how many deaths we see over the course of a minute. So I need 2 volunteers. I need one person to record the birth today number at the start of a minute and at the end of a minute, and I'll keep time. And I need somebody to do the same thing for our deaths today numbers. So can I get 2 volunteers? Nate, birth? Okay, so I'm gonna start the timer here in just a minute, and I just need you to write down the first number that you see when we start the timer. And then when I tell you to stop, you'll write down the number that you see when I tell you to stop. And then can I get somebody for the other one, Sophie? Okay, so I'm gonna start our timer here. Okay, are you guys ready? Okay, I'm starting the timer now. So go ahead and write down the number that you see right now. And then we're going to look at what those numbers are when our minute is up. And we'll use our starting number and our ending number to determine how many births or deaths we had in this minute that we're timing. We're just about halfway through. We have about 15 more seconds. And stop. So go ahead and write down the number that you see. Okay, Sophie, you did deaths, right? Okay, so what was the number that you started with? 86,611. And the number that you ended with? 717. Okay. And let me pull this down so we can see our notes. So if I subtract these, 86,717 minus 86,611, I end up with 106 deaths over the course of that minute. This is my third Algebra 1 class for today. So we also did this in 4th hour and in 2nd hour. And we saw slightly different numbers each time. I also did this on my own when I put together the notes key that you guys can access on Google Classroom. And I was close to what we had here. I had 115 deaths over the minute that I find it. And now how about births? Think, what was your first number? Okay, and then what was your ending number? Okay, and again, I'm going to subtract those. That ending number minus our beginning number. And we had 267 births in that minute. When I did this, I had 265. And so now what we want to know is what was our overall net change to the population over the course of that minute? We know we lost some people, we know we gained some people. The overall effect on the population, though, since we had more births than deaths, is going to be a positive one. So my change per minute would be births minus deaths. So 267 minus 106 would give us an overall change in population of 161 people. So over the course of a minute, our population went up by 161. Now let's take this change per minute and use it to determine what we would expect to be a change per hour. How could I do that? If I know I'm adding 161 to the world population in a minute, what could I do to determine how many people I expect to add in an hour? Multiply by 60 since there are 60 minutes in an hour. So 161 times 60 gives me 9,660. And then what if I wanted the change per day? How could I go from an hour to a day? I'll multiply by 24, since there are 24 hours in a day. So I have 231,840 people I would anticipate adding by the end of the day. Now, I do want to point out, even though this number was pretty similar, especially the birth number was pretty similar to what I had when I did this a couple months ago, our change per minute is different than what I had. I had 150. I added 150 people every minute for my net change, and we got 161. One of my earlier classes today, we had, I think, 149 people that we added. Another class, we had 165 people that we added. So it was always a positive change, a net positive change. But this number varied a little bit, and they weren't wildly different. Never have we had just 5 people that we added in a minute, and never did we have 300 people that we added in a minute. This number does fluctuate a little bit. So I would anticipate that the actual change by the end of the day is probably not going to be exactly this, but it should be somewhere in the ballpark. And then finally, our change per year. So I have the change per day. So times 365. That would be 8462160. We throw some commas in there so we can talk about this a little easier. So we're looking at, over the course of a year, having a population increase of about 84 million. Okay, 84 million. Now, let's talk about this as a percentage. If I wanted to know what percent change I'm going to see here in my population, then I need to take this change I'm expecting to see over the course of a year. That's 84621, 600. And I need to divide by the actual world population. So my actual world population, let me pull that clock back up, is 7,848,359,953. I think it was when I first got to the end of that number. Okay, so this will give me my population change as a percentage. I'm going to take the top number and divide by the bottom number. So 84621,600 divided by 7,848,359,953. And I get 0.01078. And I'll go ahead and stop there. If we round this to the nearest percent, that's going to be 2 decimal places. So we're looking at about a 1% change in our population, about a 1% change. Let's scale this to be something that's a little more manageable to think about. if we looked at a population of 100 people, what would be 1% of 100? 1. So that means if our whole population was 100 people, we would add 1 person. Does that make sense? Our school population, students, teachers, staff, other faculty members, our school population is right around 1,000, hovers just under 1,000. What would be 1% of 1,000? 1% of 1,000. 10, yeah. So for MTHS, we would be adding 10 people. Does that seem like a crazy amount to add 10 people? No, we could absorb another 10 people in our classes somewhere spread throughout the building, right? We could handle 10 more people. So if we were to keep all the people we currently have, and maybe after spring break, we had 10 new transfer students, okay? That wouldn't be crazy, right? It might be a lot if they all were in all the same classes together, but likely we're going to be spread into some different math classes, some different English classes, and that's not insane. But let's then scale it back up to talk about our whole world population. So I want you right now on your calculator to take our world population, okay? And I want you to find 1%. So multiply by 0.01. I want you to find 1% of our world population. So this number, again, times 0.01. What do we get here? What's 1% of our world population? To the 7. So you had E7 here at the end. So that means move our decimal 7 places to the right. So 1, 2, 3, 4, 5, 6, 7. So, and I'm assuming you had more numbers here. I'm abbreviating this a little bit. 1, 2, 3, 4. So we're getting about 78 million people. 1% of the world is 78 million people. Does that seem like a lot of people to add in a year? Yeah. New York City has a population of 8.4 million. So we're adding several New York cities to the world, okay? There are countries that have populations smaller. That's a lot. That's a lot. Now, granted, these people are spread throughout the planet, but that's still a lot of people when you just look at the numbers. So now this is the amount of people we would expect to add roughly in this year. And it's a little bit off from what we estimated earlier. That's okay. Let's stick with that 78 number. Let's say we add 78 million people to the world this year. Next year, we would anticipate adding another 1%. Is that 1% we figure next year going to be the same amount of people? Why not? Well, there's going to be some natural fluctuation in the amount of births and deaths we had. But I also want you to think about what next year's total population is going to be. It's going to be bigger than this year, right? Because we're adding these 78 million people. So then next year's population, which has these 78 million people added. We're going to take 1% of that. Does it make sense why that number would be different? Okay, so the population will add more people each year that it grows at this rate. It's going to add people in general, but it's going to add more than 78 million next year if we still grow at this 1% rate. And then the year after, it will add more than that. Does that make sense? Because it's 1% of that current population in the year that I figure it, okay? And that population, as we know, is always growing. So the population will add more each year because the next year's total includes the people we've added. So that 1% is bigger every year. So our world population is not a linear function because we're not going to add the same amount of people every time. Okay? We're not going to even add like within a couple hundred, probably the same every time. What we're going to do is multiply to find that 1% every year and then add that. And then the next year we'll multiply to find the 1% and then add that. So since we're going to multiply by that 1% every time, that means that we're looking at an exponential function. Remember, for exponential functions, we're always multiplying by the same amount. Questions for me so far? Okay. So now let's take a look at some snapshots of our global population. We hit 7 billion, I believe, towards the end of 2011. Let's say that our population continues to grow at the same rate. Let's say since 2011, we've been at this roughly 1% increase. Okay, we're going to use that same 1% increase that we just found. I want to know, what do we expect the global population to be when you guys will change this to high school? What about we'll do when you turn 25? Or the year you turn 50? Or at the end of the century? So what we're going to do is make ourselves a little table, because remember, we can always graph by making a table. So we're going to look at, for a few different years, what do we expect that population to be? So in 2011, it was 7 billion. We just looked at, for 2021, what was our population? Let me flip back here. 84621. So 8.4, 8.5 billion. I'll do 0.46 million. A little more accurate. And then you guys are sophomores, right? So it's graduated in 2 years. So we'll look at 2023 when you guys graduate. And then let's see, you would be around 18 when you graduate. Either you turned 18 or you're going to turn 18 the year you graduate. So then when you turn 25, you need to add 7 years to that. So 2030 would be the year you turn 25. The year you turn 50, we would need to add 25 years to this one. So that would be 2055. And then the last one we're going to look at is the end of the century, 2100. Now, one way I could approach this, and this is how we tackled our sequences in our last unit, but since I know I add 1% each time, I could take the population we have right now, find 1% and add it on, and then find 1% of that and add it on, and that would give me this population. And then I could do that 7 more times to find our global population for 2030, and then 25 more times to find it for 2055. And then I could do it a whole bunch more times to find that final population. But that's going to take us a really long time. It's a pretty labor-intensive endeavor. What we're going to do instead is take a look at a way that we could represent this information with an exponential function. So I want you guys to hop down to the bottom of our page here. And we're going to ignore this stuff in here for part B. And instead, we're going to use that space to talk about a general growth formula when I have this change as a percentage. So we know that earlier this unit, we saw a growth formula that looked like this. I equals A times B to the X. And when we were looking at graphing, which we worked on last, we also had some number potentially added or subtracted at the end that was our asymptote. This guy represented our distance from the asymptote for our y-intercept. Or when we were writing functions earlier, this represented an initial value, an initial amount. And then our base for our exponent represented how we changed that amount each time. So we doubled it, or we cut it in half, something like that. When I don't know that number outright, and we have this percentage representation instead, or this rate representation, we're going to modify that formula just a little bit to be able to include that rate. So A is still going to represent our initial amount. Our first measurement, or what we start with. And then R is going to represent our rate or percent change. And when we use it in our formula, we're always going to represent it as a decimal. Everybody have this down? Okay, so I'm going to move our paper and you won't be able to see it on the screen. Okay, so here's what I'm going to do. For our population, I'm going to do the same thing. So we're starting with a first measurement of 7 billion. And then we're increasing by 1% each year. So 1% would be 0.01 if I changed it to the decimal. And then my exponent here will be how many years it's been since we took our initial measurement. So since 2011 in this instance. So this is going to help us find those populations without having to constantly find 1% and add it back in, and then find 1%, add it back in, and 1% add it back in. The only tricky part is I need to know how many years it's been since 2011. So if I want to find the population by 2018, I don't want to plug in 2023 for X. I'm counting from 2011. So the first year, our X value would have been 0. Right now, we're at an X value of 10, right? 10 years since 2011. So this will be 12 years from 2011. Does that make sense where I'm getting these values from? So if I want to find the world population in 2023, I'm going to plug in 12 for x here. So 7 times 1 plus 0.01 to the 12th power. And we have 7.89. This seems a little funky here. It looks like we dropped in population because our estimate, right? Our 1% estimate isn't going to be constant for every like hour of the day. Does that make sense? So our total right now for our world population right at this minute or a couple minutes ago when I took that number was a little bit up. We were beating that 1% estimate. I would expect it to be about this in 12 years. We can actually plug in 10 and see what we get. So if I were to use my formula to estimate, it would tell me that I should have a population right now of 7.73. So we're beating the estimate right now by a little bit. Does that make sense? Okay. And then we're going to do the same thing for 2030, 2055, and 2020 or 2100. I want to keep going at 2021. That's not right. So what I want you guys to do now is to find the 3 remaining populations. So this is going to be in 19 years, in 44 years, and in 89 years. I want you to plug in these values for X in our formula and find those world populations. Anybody find our 2030 world population yet? What did you get? 8.46. And then how about our 2055 population? 10.85. And remember, these are all in billions. And then how about our 2100? 16.97. We'll go ahead and use our estimated number for this year, since we use our estimated numbers for all the other years. And we'll plot these. So that first year we measured, we were at about 7 billion. And then 10 years later, we should be just a little under 8 billion. In 12 years, again, a little closer, but still under 8 billion, barely. In 19 years, we're at just about 8.5. In 44 years, we should be around the 10 billion mark, just under 11 billion. And then in 89 years, we're just under the 17 mark. So we get a nice little curve here for our exponential function. Questions for me so far? Okay. Now, we estimated by the end of the century to have just under 17 billion people. Now, the UN estimates that our population is going to level off at about 10 billion by the end of the century. Why would they not follow our projection? Why would their estimate be different than ours? So things like, well, this year, yeah, right? The last year we had a pandemic that impacted our overall world population. You mentioned wars, right? World War I, World War II had huge impacts on our world population. So we can say this is kind of a downer, but things like disease and war impact our world population. But even if we didn't have some sort of catastrophic event, why might our population taper off or level off at some point? What? Why? So something else that impacts population, and scientists have done research on this with like small animal populations, is your available resources. Impact population. So if you have enough food or enough shelter, enough space for 10 billion people, then your population is going to level at 10 billion. And it might hover a little above and a little below sometimes. But if your available resources support this amount of life for this amount of animals or this amount of people, then that's probably where your population is going to taper. Questions for me on our population example? Okay, so the last thing I want to look at for today. And one more comment about models. Anytime we look at a model, that's what we created here with a model for our population. Anytime we look at models, they're generally pretty good for predicting the information around the period where we collected data. So our model should match our initial year pretty well. It should do okay. We saw kind of a fluke today. I will say for my morning classes, our number here was a lot closer to the 7.7 than what we had here. Should do pretty well for, let's say, 2015. It probably even is fairly accurate for 2023. Maybe for 2030, but at this point, we're getting pretty far away from where we took our initial measurements. And until we're able to take more accurate measurements closer to 2030, I would put a question mark next to that number. I would guess that our number for 2055 is probably not accurate. And I would guess our measurement, our guess, our estimation for 2100 is also not accurate. Models are really good for making predictions during the time where I've gathered data, immediately before that time and immediately after. But far outside of that time where I've gathered information, usually that's where they get a little fuzzy. So what we're going to look at next is a few more problems where we're looking at and using this sort of general growth formula. So if you would, for me, please turn to the next page. We're going to set up a couple problems together on page 14. So for number one on page 14, we're looking at an investment. The purpose of an investment is that you start with some money and you make some more money, right? You want your money to be increasing. So we're going to determine the value of an investment of $2,500 that we invest at an annual rate of 5.25% for 4 years. So the first thing we want to do is create an exponential model to sort of summarize what's happening here. That way, just like with our population, we could plug the year we wanted into our formula, excuse me, to be able to determine that amount we have. So I'm going to start with my function. Remember, we're looking at that general growth formula. So I'm going to start with my initial amount, 2,500. And then I'm multiplying by, in parentheses, 1 plus my rate as a decimal. So we've got to move that decimal 2 places. So 0.0525 to the x. And then since I want to find out how much money I'll have in 4 years, I'll take my formula and I'll plug in 4 for the exponent. And that will give us our amount in 4 years. Now there is a tweak I could make to this function. Right now in parentheses, I have 1 plus this decimal. If you want, you can also just add that together. These functions are the same. I've just gone ahead and done the addition with that bottom version. So both of these are correct. They mean the same thing. So if you saw this version, it means the same as this. Questions on number 1? Okay. And then let's talk through the setup of number 2 as well. So number 2 says we have a population of 100 frogs and it's increasing at an annual rate of 22%. We want to know how many frogs will there be in 5 years. So I'm going to help you with the equation on the second one. So that would be y equals 100, since that's our initial amount of frogs, times 1 plus 22% is the decimal, so I can move the decimal 2 places, so 0.22 to the x. And then you would plug 5 in for x to figure out how many frogs you have. And then again, the other option you have would be to add the 1 and the 0.22 to get 1.22 as the base for your exponent. I want you guys to go ahead and finish the problems on page 14. Okay, so you need to give me that function that models what's happening there, and then also answer the question. You need to go back for number 1 and find that amount. For number 2, you need to tell me how many frogs we'll have. For 3 and 4, I think they're both a dollar amount. How much money will you have in a specified time frame? Okay, so that is it for today, and I will see you guys tomorrow.